So for this week's celebration of learning, we've been asked to model the total energy of a hurricane. We also have to make a model where we can estimate the total energy of the system at a particular instance in time. So in order to properly do this, we have to first define what exactly is a hurricane and some of the other parameters, so that then that way we can provide a reasonable solution to the problem at hand. So, my definition of a hurricane is that it's a cylinder of rotating air that's based about two circles. One circle in the middle, which is the eye of the storm, and various, and sorry, not two circles, it's multiple circles. One is in the middle, but then there are other circles that incrementally decrease in speed as they increase in the total amount of radius away from the center of the storm. And with this being said, we can now start to define what our hurricane system is. And so to first figure out how big the hurricane is going to be, according to this source, the Weather Research Center, it gave a few different examples of a variety of diameters of a hurricane. But I chose my hurricane to have a diameter of 500 miles, and for it to be a Category 4 hurricane according to the Saffir-Simpson scale. And the reason why I did it this way is because with 500 miles, I was able to easily get 500 shells originally. So, not 500 shells, 5 shells were 100 miles in diameter for each shell. And so on the outside, I calculated what it's not shown here, but the average velocity of a tropical storm before a hurricane is classified as a hurricane, which was on average 56 miles per hour. And then for each of the different layers, I went through the averages of 1 through 4 in terms of miles per hour. And then I also assumed that the eye of the hurricane was negligible, that it had to be taken out of the total area of the total amount of the hurricane that's actually doing something. And I used this model, in part the dissipation model, because I felt that the total energy of the hurricane's rotating motion was the kinetic energy that it reached, which was equal to the dissipating rate of all of the rain and everything else that's spinning with the hurricane. So this formula is given that the dissipation rate per unit area was the air density times the surface drag coefficient times the velocity cubed. And this article gives a good definition where the power is equal to 2 pi times the integral from 0 to a set radius of the hurricane, or whatever circular system that I'll be modeling, and give it to multiply by the air density, the surface drag coefficient, the velocity cubed, and the radius for that function. This is a good model, however, it is an estimation. It is a simple estimate. This means that this model is actually not the best for the scenario. What I'm doing, I had to adapt it. I felt that the hurricane is in different layers, and increases in velocity as you get closer to the center, which follows the conservation of angular momentum, because as the total momentum of the system, which is the hurricane, is conserved. But as you go further into the hurricane, you have a smaller radius, and since you have a smaller radius, you have to have a faster velocity to make up for that momentum. And so in order to calculate this, I decided to take this integral for different parts. So for the first 100 miles of diameter, I had it set to a tropical storm speed, and then added the integrals as I got closer to the center. And then when I got to the center circle, I had to subtract out the eye of the storm, which was about 30 miles in diameter. So with this being said, it's partially there. We're partially at a good model for recreating this. What this one lacks is that it is only two-dimensional. It is for a circle that is dissipating at that rate, not a cylinder. So what I decided to do was I took the double integral of this function, of this formula here, and I made the air density a sort of y function, while the radius would be an x function, which you'll see later in the software, which I use to calculate the values. And this was good because I felt that the velocity would remain the same and the drag would remain the same throughout the hurricane, or rather the velocity would change depending on which level of the hurricane you have reached. So these values would be inputted differently every time, as well as the bounds for the radius would change every time. But the air density is a number that fluctuates depending on how high up on the ground you are. So at surface level, it is 1.225 kilograms per meters cubed. However, the height of a hurricane is 50,000 feet high. So I found what the air density would be at 50,000 feet, which was 0.01027 kilograms per meters cubed. I also needed to find the proper drag coefficient, and so since a mature hurricane is nearly circular in shape, I decided to take the drag coefficient of the cross-sectional area of a sphere, which I found to be 0.47. And now I also converted all the mile measurements into meters and miles per hour into meters per second, and divided the total diameters to get the radii of the different systems. And so I then took the double integral of 2 pi times the bounds, which I set for my y function, which was the air density from the air density at the ground, which is 1.225 to 0.01027, and the integral of the bounds for the radii, which changed every time I wanted to get a new measurement. So this was 250 miles converted into meters, which is the 402,336. And so my integral is y times the drag coefficient of 0.47 times the velocity of the tropical storm, which was 56 miles per hour, converted into meters per second, was 25.0342 cubed for the model, times x, and I just subtracted it from the double integral of where the radius is now just, at least it's going to be 50 miles less than what it was, so it can be incremented properly for 5 different levels, 50 miles for each level. And so I calculated the value I got for each ring and added all of the rings together. So I got a value here of 1.01284 times 10 to the 15th. I did this 5 times for the 5 rings for the category 4, and after getting a variety of values, I added them all together and got the total sum of 1.228948 times 10 to the 16th in watts. And in order to make this value be able to be determined at a particular time, because that is one of the requirements, is that you have to estimate the total energy of the hurricane system at a particular instant in time. You multiply that value by whatever time stop you want to use. So if you say that you can multiply each one of these values by the particular time stop. So if you're saying that the total hurricane will be completely gone in 24 hours, and you are looking at the first hour, then you take 1/24 off of the total of each one of these integrals, and then add them together to get the total amount of energy, which will still be significantly high, because as of right now, it's 1 times 10 to the 16th watts is very high, which is understandable because in retrospect I found that my model for the hurricane was slightly large, particularly for a Category 4. Thank you very much.